All right, let's get started. So, welcome to our webinar on finishing methods. A couple housekeeping things. If you have the side-by-side view in your interface, your Zoom interface, then from time to time, we'll show some parts. So it might be useful to be able to see both the talking head window and the slides. If you have questions along the way, feel free to enter them into the Q&A panel. All right, so let's get started. Talk about finishing methods for metal 3D printed parts. We'll talk about why post-process at all, and then about the various methods to post-process. So they're everything from green sanding the parts, some methods specific to metal 3D printing, as well as just general finishing methods for metal parts and the suitability of those methods for metal 3D printing. So with that, let's get started. First, a little context. Desktop Metal, our mission is to make 3D printing accessible both for the early stage of the product development life cycle, so engineers, designers, but also for manufacturers, so you can manufacture actual end-use parts and produce parts, whether they're small parts, large parts, by the thousands or millions if you need. Some of our customers, you'll recognize some of the logos, many you won't recognize, and that's kind of the point. The metal 3D printing technologies have come a long way, and so now they're quite accessible in terms of both cost, ease of use, broad breadth of applications that they can be used successfully by companies large and small. And we've brought to market 3 different systems. Studio system for office-friendly prototyping. So that's the system right behind me. That's you wheel it through the door, plug it in, and start printing and sintering. And then there's for larger volumes, including batch production, mass production. There's the shop system and production system. And we'll see parts from all of those systems and how the different finishing methods work for them. So first, the need for secondary operation. It's worth saying that really not everything requires post-processing. There's plenty of parts that they come out of the furnace. The part as printed and sintered works just fine. On the other hand, there might be applications where, for one reason or another, you might need to do some post-processing. So we'll talk about that, but it could be, depending again on the application, the dimensions, the design characteristics, that the part works just fine. Now, what are the characteristics of metal 3D printed parts? Because they are somewhat different than, let's say, parts that are machined or parts that are cast. First of all, what do you get? You get a part that is near net shape. So it's close to what you need, maybe even works just fine. So here's an impeller printed on this, right on the Studio system. And you know what? This impeller will work just fine if you plug it into this into the machine that it goes in. And so with 1% or better tolerances for many applications are fine. But if they're not, then you may need to do some post-processing. And so 3D printed parts do show some visible build lines. So here's a centered part, and you'll kind of see the layers. This is the printing orientation, prints layer by layer. And so you can see visible layer lines. If you need to get rid of them, a few different options. Surface roughness is considerably lower than powder bed fusion, another common way to produce metal parts, but it is rougher surface than standard, ground or milled or turned parts. So for example, the surface roughness of this part, it's quite smooth, definitely smooth to the touch, but it'll be probably 3 or 5 micron average roughness, whereas machined parts are going to be smoother, maybe by a factor of 5 or even 10. And there will be, depending on the printing technology, some imperfections. You might see build lines. There might even be, depending on the geometry, some burrs that you may want to get rid of. There also may be some oxidation just at the very surface, and so literally a couple microns worth, even though something you might print it as stainless steel in the furnace, some of the chromium might have evaporated from the surface. And so literally there might be just less than a micron kind of oxidation, but that's easy to get rid of with, say, media blasting. We'll talk about that as well. And it is worth saying that of the two different approaches, the studio system and then the binder jetting solutions from the shop production system, the binder jetted parts do have even better surface characteristics than the studio system parts. So for example, this is a part printed on the shop system. You'd be hard pressed to see the lines, the layer lines, and this is quite a smooth part. Contrast that with, let's say, this part, still smooth, but you can definitely, especially on the support side, see some build lines, toolpath kind of lines, and some imperfections. So that's kind of what you get with metal 3D printed parts. It's worth showing this comparison. I mentioned surface roughness. It's not the only reason you may want to get rid of, or you may want to do some post-processing, but roughness could be one. And so as sintered, you might have a roughness of 5 microns. And then depending on which finishing method, you can get 5 times, even 10 times, or 50 or 70 times smoother. For example, CNC machined parts, you might have half a micron kind of roughness versus isotropic super finishing. So this is one example. So this is a bracket for a motorcycle. Here it is resting on the support as it was printed on the studio system. But the part was also post-processed with isotropic super finishing. We'll spend a little time on that as well. And you see, you get remarkably, it's 150 nanometer kind of finish, which is insane. It's even smoother than machined parts. All right. So there's a bunch of reasons to post-process. Dimensional accuracy is one. Surface roughness is another. You might have internal channels. For example, here's a copper heat exchanger that has internal cooling channels and some fins, as you can see. And so you may want to hone or smooth out the internal channels so that whatever fluid flows through there flows with less resistance. And there could also be aesthetic considerations. Maybe you're printing prototypes of lipstick holders, lipstick cases, see, fully functional. Or you might have shift handles. See some of these examples finished in different ways. This is black nickel, this is gold plated. You do nice chrome kind of finish. So there could be aesthetic considerations and other functional requirements. Maybe you want to passivate a surface, for example. So let's begin. Let's look at a bunch of these different finishing methods. So first is green sanding. What's green sanding? Well, the part when it comes off the printer, where's the printer? It's the one right over here. That's the printer. So when it comes out, there are minor imperfections in the printing process that you're going to see. And it actually turns out it's a lot easier to get rid of these imperfections while it's still in the green state. So prior to sintering. In the green state, it's got the consistency of a crayon. And so a crayon is much easier to cut away, smooth out with, let's say, well, we'll talk about the different methods available. But so for all these artifacts, if you don't remove them at the green state, it'll be a lot harder, 10 times harder, 10 times longer to get rid of them once the parts are metal. And so to the extent possible, if there's any obvious imperfections, green sanding is something that we recommend. Green sanding, this is a process that smooths out the build lines, the toolpath artifacts. It's performed after the printing process, and you can save a lot of time. Really, you can almost eliminate the appearance of the layer lines, and you can get a surface finish that's actually much smoother. I'll show you an example. So here's a nozzle. This is a standard part of a machinery. This is the part that was printed. And so what's important for this nozzle, and I think we see this example in a few slides, is through this channel flows, or I'll show it not connected to that. There's an interface. Through this channel flows a ceramic slurry that's thick, it's abrasive, and it flows better. This is an extruder that out of this rectangular part is what what the goal of the slurry is to be formed. It's like a pasta maker, except you're creating a shape, that shape with ceramic, thick ceramic mass. It flows easier if the inside is smoother. And so being able to polish this or sand it in the green state, you can achieve much smoother surface in here than with the standard part where you can actually kind of see the build lines. So that's an example. We recommend sanding of these green parts to be inside a fume hood or a downdraft table that basically ventilates and captures the dust to minimize the airborne dust from the sanding process. What can you use? Well, Scotch-Brite, you know, you might use this on your barbecue grill. Well, you can also use it on your on the green printed parts. So the abrasive hand pads, for simple imperfections, you can just polish them. And then you can use sandpaper in a variety of grits to, and you know, just you might progressively go initially with a medium grit, then fine, very fine, to really smooth out. It really depends on how much you want to get rid of. And the trade-off here is sandpaper can get rid of the material pretty aggressively, so you actually want to be kind of light with how much you use it. Here's a little video. By the way, if there's questions, feel free to ask them in the Q&A portion. So here's an example of a green part getting sanded. You can use a detail razor to clean up some of the edges. So you can see that depending on what the imperfections are and what you need functionally from the part. So that does some amount of cleanup. And you can even use a brush to get rid of debris. So depending on how much debris there is. This is mostly necessary not for the mass production, you know, shop system, production system. This is more for the studio system, a kind of extrusion-based shape creation, where this might be a useful technique. So that's brushes. And the example, so this is that very nozzle. Here's the interface. So with a gasket comes on through here. The twin ceramic extruder pushes the ceramic slurry, and the less friction inside the channel, the better. So, so the green sanding was great as a way to get a remarkably smooth internal surface. Okay. Next is media blasting. So media blasting, this is a great way to remove surface imperfections with, so it's your part is inside a cabinet, or you can put a bunch of parts inside the cabinet. And then you, under pressure, propel the blast media, which could be glass beads, it could be a loose ceramic alumina, it could be steel shot. They all have kind of different, different results. And so, for example, the spherical glass beads, they impinge on the surface, they produce a very small dimple, and this dimple behaves like a concave mirror, and so now you have a much more uniform kind of satin sheen to the parts. So some examples, here's a part that was sandblasted. This is quick enough and easy enough that really we recommend doing this with most metal parts. Now, if you're printing a part, then it's going to go into the bowels of some equipment, never be seen again. Doesn't come in contact with people for the most part. No problem. But it could be useful to just do a quick media blast. The applications are, you know, to matte, to bright, on the surface finish for aesthetic appeal. You can remove corrosion. That's a great way. You know, if there's you know, a few hundred nanometers, not even, it's probably tens of nanometers of oxidation on the parts. Sandblasting or with steel shot, for example, could be a great way to get rid of it and blend the superficial scratches or tool marks. So I'll show a little video of that. Turn down the volume a little bit. You see this is a part, and the pressure, it's operated with a foot pedal, and so you just put the part underneath, and under pressure inside this cabinet, direct the flow onto the part. So Even with a little media blasting, the parts will get a uniform finish, get rid of the any oxidation or surface imperfection, and really it doesn't impact. It's a mild enough treatment that it doesn't impact dimensional accuracy on the part. You're not removing, you're not removing tens of microns of surface, for example. And you can use lower pressure if you just want to change the surface appearance, and you can use glass beads or stainless steel shot if you want to be if you want to remove more material. Few examples, most parts leaving Desktop Metal get some sort of a blast, even if it's, might be a crankshaft, or it could be a gear. This is going to be a Sun gear inside a giant earth drilling equipment transmission gearbox, or this timing belt pulley, one of our customers printed for their manufacturing floor. So the parts, whatever the part is, spend a few seconds and media blast, you'll get a more uniform finish. Recommend that the cabinets are low cost enough that it's kind of almost a no-brainer. I think if you're going to be doing a fair bit of metal 3D printing, that's a great thing to do. Put the parts through. Fortune Metal Finishing has a great blast cabinet solution designed specifically for Desktop Metal. We work with that team a lot. It's a great cabinet. We have one here. And so at fortunemetal.com, you can see they have information on the blast cabinet itself, as well as an application note on what the benefits are of air blasting and trade-offs and different media finishes and what they get you. Next, kind of a logical progression from media blasting is let's talk a little bit about tumble finishing, vibratory finishing, and high energy finishing. So what are these methods? So this is a group of processes where, with relatively low energy random motion, so it could be spinning in a kind of moderate speeds, or in a container that's a vibratory bowl that's getting shaken. Basically put the parts in along with some abrasive media. And so it could be the abrasives, could be some fluid to make everything kind of circulate evenly. And you agitate this container with some sort of a mechanical method. This is great. This is a great thing for mass finishing. So you got a whole lot of parts you want to finish. You throw them in for hours, or it could be a day or two even. And then it works, and by mechanically putting the abrasive media against the work pieces, they'll become smoothed out. So you'll blend edges, blend away imperfections. It's great for geometrically simple components. Why is that? Because if you have internal channels that might be harder to get into, you'll have non-uniform ways that you'll remove material. For example, if you take this part, depending on how large the abrasive media is, it'll have pretty easy access to the outside of the piece, but maybe inside it won't get into as easily, and so it'll wear away the outside more than inside. But really, it depends. It depends on what are you trying to accomplish. If you're mostly trying to get rid of sharp edges on the outside, this is a great way to do it. And also in part, you can still get great great finishing from just tumbling parts. So you can get both smooth and visually appealing kind of finish. You can do pin finishing. So if you have small parts, whether it's jewelry or other parts that are relatively small, you can have. So this is a small container. There's pins inside, hence the name pin finishing. There's a magnet. It spins, and as it spins, the magnetic media follows it, and so you have this kind of circular motion. And the rotation of the magnet, spins the media. The media then deburrs the parts, the work pieces inside. And then this process can also be extended to much larger parts and larger volumes of parts. So you can do batch type finishing. It's hard to tell from this picture how big this part is, but actually a 5-6 foot human can stand on just this platform. So this is a pretty large part of pretty large piece of equipment that's could be 8, 10 feet across. So this is great for batch type finish processing, where you have a lot of parts, you have abrasive media, and it's open, and so you can monitor it. You can literally see, okay, what's happening with the parts, inspect them, and that makes it that much easier because you throw it in the beginning of the day, check at noon, how are the parts, are they shiny enough, are they smooth enough, and then take it out when it makes sense. Next, an extension of that, kind of on steroids, is high energy method. So this is, conceptually, it's similar to the vibratory method in that you have the part getting polished, you have the abrasive media, and you may have some fluid inside, but this is put inside a closed system that is then spun very fast. So that's the name, hence the name centrifugal disc. Centrifugal barrel. The parts are getting spun much faster, and so the abrasive brushes past the parts at a much faster rate than with the vibratory bowls. And so as a result, your material removal rate can be 5, even 10 times faster. So that's it's a dramatic. It really uses a lot of centrifugal force and this mechanical advantage to take away material. And so it's much faster, but you have the trade-off is you may have less precision with how the material is removed, and you definitely have the same unevenness where, depending on, if you have internal crevices, for example, the abrasive media wouldn't get in there with the same kind of speed. So, but if you want to remove a lot of material, you want to do a lot of polishing quickly, this is a great way to do it. And there can really be different formulas. And so that's kind of what you're seeing here. 2 very different ways to process. Here's a hinge that was 3D printed, and 2 different approaches to kind of different recipes, each with their trade-off. So in the one on the left, you have a wet cut with a Duramedia. It's a premium ceramic formula designed for hard alloys. And you can run with this kind of media for 20 minutes inside a centrifugal disc, and then a wet polish for another 10 minutes. So really, it winds up being a 30-minute process. And you go from this kind of rough and fairly matte process to a smoother and a shinier part. And then you can spend, here's a different formula, with a process that takes just over 2 hours instead of 30 minutes. So this is 3-step process where you got the same wet cut media for 60 minutes instead of 20. And then you have a wet cut with a plastic media for another hour. And then there's a wet polish. So altogether, just over 2 hours. You see, there's this trade-off. The part that is considerably smoother even than the previous part. You're starting to see, though, some edge rounding. If what's important is the sheen and the smoothness, then the one on the right may be the right thing. If you want design integrity and you want to maintain the exact dimensions and angles to what you printed, then a shorter process may be better. So this is kind of the trade-off. And these are just a couple examples. There's a number of, depending on what you're trying to achieve, a bunch of different recommendations and recipes that may work. All right, let's extend these 2. So now we talked about vibratory bowls and high energy disc. Natural extension is isotropic superfinishing. And what this does is this process combines those mechanical finishing techniques we just talked about with an active chemistry compound. This chemistry compound is designed to react with the surface of the part, and so just the surface of the part. So here's a great example of it. The part started out with literally this exact kind of, matte surface where you can see the layer lines. It's immersed in a fluid. That fluid reacts with the part that's started out with this kind of finish. And then by reacting with it, just that top surface becomes soft. It's like a conversion coating, becomes soft and much easier to remove using the vibratory bowl or the high energy disc method. And so you wind up with, it's basically a way to, well, we'll see on the next slide exactly how it works. But this is a way to reduce the required forces necessary to get that smoothness, while still not removing a lot of material. And so you maintain the traditional, you maintain the geometry that you're printed in, but you still wind up with a very smooth surface. With the previous processes, if you wanted to get the very smooth surface, you'd wind up actually removing possibly half a millimeter or a millimeter or even more off the surface. So your design really, your part starts to change geometrically. Here, you're removing much less, yet still achieving this kind of finish. So let's take a look at exactly how the process works. So it's kind of a two-step process that continuously takes place. And I should mention this was really developed, pioneered, commercialized by our friends and partners at REM, Surface Engineering. So here you have a chemical surface activation where you have some surface that you start out with a surface that's can be rough. And then there's a process chemistry that reacts with a thin layer of this surface, creates a conversion coating that's now soft, relatively brittle, easy to remove with a lot less force than we normally would. And then there's the continuous mechanical rubbing. That mechanical rubbing removes kind of the stuff off the very top of the surface, what's at the top, the peaks. So the mechanical rubbing removes the peaks, not the valleys, the peaks. And so, but then remember, you got these peaks, they're still in that liquid, and so that surface activation that forms, that reacts with those peaks, forms yet another coating, and so the peaks are gradually worn away until you wind up with very smooth surfaces. And so the end result is parts that have that mirror-like amazing finish with 100 nanometers or even better kind of surface finish, but with a much faster time and reduced geometric alterations. And so there's a bunch of, and also this is great for non-uniform kind of parts. So if you want to, so this is an example of a cylinder or piston head. The material can get into all the nooks and crannies, and so if you have internal parts you want to get in, this is a great way to do that, and this is suitable for both large and small parts. The applications, there's a few applications. One is when you want to alter the surface texture. But also there's mechanical and other functional benefits. For example, it could be biocompatibility or surface cleanliness. If you have a roughness of 3 or 5 microns, maybe that's an opportunity for some problems to form depending on if you're in a chemical or food preparation kind of environment. And so you can get cleaner surfaces that way. It turns out that bending fatigue, because you've smoothed out, there's now no sharp notches. Everything is smooth radius. The crack propagation that happens in sharp corners is reduced, and so the fracture bending fatigue is a lot better. This is important in a number of applications, including, let's see, I have the example somewhere here of gears. And so if you have gears, well, we'll get to it in a second. But so gears or actually assemblies move smoother relative to each other. This is an example of a part of, in this example, it's chainmail, kind of make the point of how fine a set of assemblies you can print inside as just as one print. So this is chainmail with all the links printed. If you smooth using the REM process, there's a lot. They move a lot easier. There's no little notches for them to get caught on. And so for a whole bunch of reasons, whether it's airflow, corrosion resistance, surface texture, so isotropic superfinishing is a great method. Ring splints, here's a great example. So this is a ring splint. It comes out fairly smooth, but there's still some notch, some roughness that may not be as pleasing to, on your limb. And so with isotropic superfinishing, you can mass finish these and turn them into incredibly smooth surfaces. Kind of as an extreme example of what the REM team has done for NASA. So here's a copper alloy combustion chamber for liquid rocket engine. Started out with a surface roughness both inside and outside of 15 to 20 microns, which is just kind of typical. Well, with the REM surface process, they could get it down to almost 100 times smoother on the outside, less than a quarter micron on the exterior, and 10 times smoother, better than 10 times smoother on the inside, less than a micron and a half surface roughness. So pretty remarkable results. When you're choosing, there's a lot of variables here, a lot of options, a lot of knobs to turn, and so REM is a great resource. There's a number of considerations, both what you need from the desired part in terms of desired, what kind of surface condition you want, the costs, the geometric complexity of the part. Is it complex, not complex? And there's a bunch of equipment considerations. There's trade-offs between process, how flexible the process is to different kind of parts, different chemistries. Some parts are easier to run, but it may be there's trade-offs with process time, with process cost. So REM is great for guiding you through that. And there's kind of two ways to work. One is you just send them the parts, and they send you back the shiny, amazing-looking parts, or they can have installed solutions. And so that's actually what we have at Desktop Metal. We have one of these REM systems. They've worked with us to fine-tune the process, the media, get the whole formulation right. So there's both ways to work. If you have just a few parts, send it to them. If you have a lot of parts, you're finishing, you think Craftsman wrenches and sockets are mass finished this way, then it makes sense to bring it in-house. All right, next, let's talk a little bit about extrusion honing, also known as abrasive flow machining. What is this? So this is a method, extrusion honing, or synonym, abrasive flow machining. This is needed when you have internal channels, in particular internal channels that curve, and you have a process, you want to smooth out the internal channels. That channel might be long, it might curve, and so there's not an easy way to get in there and really smooth it out. And you might want an incredibly smooth finish. Maybe the surface roughness, normally you print something 5 or 10 micron average surface roughness, maybe inside the channel functionally, you want to really have it be smooth 10 times smoother than that, 20 times smoother. And so a way to achieve that is by this unique process. This is a process that takes a viscous media and adds abrasive to it. And so this viscous media is kind of the thing that pushes by under pressure, the viscous media combined with this abrasive media. It's almost like, imagine if you could take sandpaper, take just the abrasive parts of the sandpaper and load this slug of viscous media that pushes the slug through. This is a great way to get, it's actually quite broadly applicable. I'll show a few examples of that. If you have, for example, you have a vehicle and you got manifolds, by smoothing out the internal channels, you can actually get 20, 30 horsepower, which matters if you're building a racing engine or a dragster. And so first I'll show the process. So this is kind of cool. So watch this. This is a part with internal channels, and now you're going to see machine's getting turned on, and now this clay media under pressure is getting forced through, and this media is loaded with an abrasive material. And so as it gets pushed through, and by the way, that material, that slug is entirely recyclable, and so you can go in and get pushed through under pressure. I'm going to run it again because I think it's so awesome and mesmerizing. So when you want, whether it's aerospace application, automotive, tooling, or just parts, and I'll show a couple of parts, but like the internal cooling channels of this heat exchanger, or you have extrusion dies that you printed, it's a really great way to make internal channels smooth. So the company that pioneered this process is called Extrude Hone in Irwin, Pennsylvania. They got offices all around the world, but this is the headquarters. And they run, whether you have 1 or 2 parts, they can do a little contract for you. They sell capital equipment, and then they'll help you service and provide the media for that. So this is a great way if you have internal channels, you have parts that you really, you want the internal guts of them smoothed out. In our case, so here's an extrusion die for familiar like 80-20 kind of shape. This is an extrusion die printed on the Studio System. You can use it to extrude, could be plastic or it could be aluminum extrusions. What you want in order for that molten or very hot shape to be flowing well through that extrusion, you want very smooth channel. And so this was extrusion honed, the internal channel of the die. So you see how this is like a mirror finish inside. And that's, so you can achieve that, and now you have a better functionally performing tool and die, or tooling. Next example, we're just breezing through these. Let's see how we're doing. Yep, doing good on time. Electroplating and electropolishing. So let's talk about that. So what is this? So electroplating, this is a process that uses electric current that reduces dissolved metal ions that are positively charged onto your workpiece. Your workpiece becomes an electrode, and these positively charged ions, by passing current through this solution, they actually get deposited. So here you see a whole bunch of examples, parts, steel parts, 17.4, and 316L parts, plated with gold, with silver, with nickel, so a bunch of different finishing methods. I'm going to show a couple of them live. And there's actually a lot of examples, a lot of reasons why you may want to electroplate parts. By the way, you can electroplate these parts. There's nothing specific to metal 3D printing. These parts can be machined, or they can be the parts you printed. So just like you can plate, just like you may plate today, parts that you machine or cast or however you get the parts, same ways you can electroplate parts that were 3D printed. A lot of reason could be wear resistance, could be corrosion protection. You know, you put nickel, put gold, the part becomes doesn't oxidize or other kind of corrosion protection. Maybe you care about how smoothly parts slip relative to each other. So you might have a very hard part. Maybe it's made of tool steel, but you want to have a plating that's actually softer, so that the very top is somewhat soft, so parts move relative to each other. Or it could be solderability. That's why so many contacts get nickel or gold plated in the electronics world. And so a lot of our parts have been plated. I'll show just a couple examples. These are guitar tailpieces. They all started out as printed steel parts, but maybe for aesthetic reasons, you want to plate them in whether it's copper, gold, black nickel, other methods. Gold plating, some great examples. You got these lipstick holders that you see here. Whoops, that's all right. This finger splint you already saw. You can print, by the way, whole assemblies. So this is a nice little assembly printed as one piece on our binder jetting solutions. So you see the wheels turn. Started as steel, you can gold plate it, no problem. All the way to, let's say you have custom shift handles that you want to plate. So here's a gold plated shift handle, or if you want to plate it with black nickel. So this is the beauty of, you can choose the design, you can do mass customization with the shop system or the production system. Print 1,000 of these at once if you want. They can all be a little bit different. You can have 5 flavors, you can have 100 flavors, and then they can be finished in a variety of ways. And so you see all the different kind of patterns and finishing methods. So this is now a very straightforward thing with metal 3D printing. So that's metal 3D printing. The other, that same process in reverse, run in reverse, actually removes material. So electropolishing is a great way to run You got similar bath, but running the current in the other direction, you actually remove material from the surface of your workpiece. Why do you want to remove the material? To reduce the surface roughness typically. So level out the peaks, the valleys. This is great. This is another great way to polish irregularly shaped objects. So if you have internal, let's say I wanted the inside of this bulb nozzle. So the inside of it, it's hard to get for abrasive media. By electropolishing, if you really cared about the inside being smooth, electropolishing is a great way to do that. And so that's electropolishing. Let's talk a little bit about machining, grinding. The parts, so this is a burner tip for a combustion engine. The part normally would be cast. It was 3D printed on the Studio system as a replacement part for a part that failed, that was cast in 1967. So a part from 1967, it's 53 years old today. Part broke. The original casting tooling is not around. The company that cast it is not around, but as a replacement part, you can now 3D print on the Studio system. What's my point? The point is, this part does not need any post-processing. It works as is, dimension-wise. But you could have a scenario where, let's say you have a gear where the keyway or the internal, let's say the bearing or the parts that this gets mounted on is a very precise, needs a very precise tolerance. Or you might have tooling that in order to fit, you have a mold insert that in order to fit really needs to meet very tight tolerances. Of course, you can CNC or EDM or grind, and this is examples, you're seeing examples of 3D printed parts here that are getting EDM'd or ground. Great example is, where is it? So here's a lathe gear. It turns out the internal surface of it needed to be both smooth and dimensionally extremely accurate to fit on a particular shaft. And so here's the gear printed to near net shape. The teeth actually work fine without any sort of post-processing. But in order to be mounted here, the part needed to be both smooth and extremely accurate. And so for that, machining it was a necessary thing. Another great example of machining parts you print. So here's a company, Ewall in Milan, Italy. They're a leading vendor of high-tech propellers for high-end sailing yachts. And so they have this propeller pinion, which connects the propeller shaft to the blades. And the goal was to streamline manufacturability. Typically, these pinions are made via investment casting in large lots, and then there is machining that takes place after. So here's an example of the propeller pinion. Here it is printed as one piece instead of, printed in lot size of one instead of, on demand, instead of the casting lots, which have to be typically like 100 pieces. And you need wax, mold, preparation. There's a whole setup required to produce these, typically via casting. With 3D printing, you print the part, sinter. So what you're seeing here is the shrinkage in the furnace. Don't worry, the software takes into account the shrink by scaling the part up appropriately. And then the part is, the blank is machined. What's great here is by printing the part much closer to the final shape, there's actually less machining required. And you see these are the machined surfaces, and the part works great, part works fine. And so now you have, instead of casting and waiting for the whole casting operation, alloy procurement, wax setup, tooling, you can just simply 3D print on demand what you need. All right, so that's machining, grinding. Now let's spend just a second on heat treatment. Decided to sneak this one in because it's kind of a post-processing of the parts. So there's a bunch of applications where you care about the hardness of the parts you're printing. Typically when they come off the studio system or the shop or production system, they come out of the furnace, they have no memory of the shape creation process, which is, in a lot of ways, this is an advantage. The parts are isotropic in X, Y, and Z, similar characteristics. You literally can take a slice and you cannot tell from the crystal structure or from the grain size, what the image looks like. You cannot tell the printing orientation. But one of the consequences of them coming out fully annealed is they're relatively soft. So relatively soft could be 27, 30, 32 Rockwell C hardness. Now, for many applications, that's perfectly fine. But if you want real, even higher, more hardness, whether it's tooling applications or other reasons you might need something to be very hard, you may want to harden the parts. And so the good news is the parts you'll print, whether it's on the studio system using bound metal deposition or on the shop or production systems using binder jetting, the parts are totally heat treatable using the familiar ways you might heat treat parts that are wrought. H900 is a popular process. Here's a couple examples of the material properties. So you see 4140 chromoly steel and H13 samples. So for example, with the H13, notice as sintered, you have a yield strength of 650 megapascals. It almost doubles when you heat treat it. Almost doubles. And the tensile strength before it ruptures goes from 1300 to over 1700 megapascals. So really the parts go, and Rockwell C going up from 35 to 45. So this is a significant jump. 4140 chromoly steel, once you've heat treated it, you have yield strength of over 1,000 megapascals, so a gigapascal, more than a gigapascal, which is pretty crazy. And the Rockwell C as heat treated for 4140 is 40. So you can get some great parts. Show a couple examples. So this is a blacksmith touch mark. So it's kind of like a brand stamp for a blacksmith. So this is printed on the studio system in H13 tool steel, hardened. And here he is branding. I'm going to play this video so you can see how he's branding this very hard part. He's taken his brand and whacking it with a hammer. That part that imparted that stamp was printed on the studio system. It was H13. So we're going to see it close up in a second. So think about the kind of the crazy heat, the forces involved. No problem with this. So here's once the part cools down, here's what it actually looks like. So here's the stamp, and here's the part. Not an everyday application, but kind of drives home the point of heat and forces involved with these parts that you can 3D print. Another great example of when do you need hardening is here's gear for earth drilling machinery. So these are machines that are a couple stories high that drill giant holes in the earth. And at the heart of these machines is this is a gearbox. There's a gearbox, and there's a sun gear at the center of it. So this transmission gearbox with the sun gear, it takes 3 months for that. If you order that sun gear, it takes 3 months to get it from China, from the foundry in China. Instead, you can 3D print it. 3D print it. Here's the part. By the way, you can print parts that are, oh my God, even bigger than that. This is kind of an insane example. This is bigger than my head. So that was printed on the shop system. So that's pretty amazing. This thing was printed on the shop system. This part was printed on the studio system. Why am I telling you about this part? Well, because this part, when it's mounted and interacts with the other gears, it's got to be right at the teeth where they're making contact. It's actually quite important for this gear to be very hard, in terms of Rockwell C. So that it's not soft here and can really, it doesn't spin fast, but it's important. It transfers a lot of forces. And so here's a certificate. I'll point out a couple things. First of all, so the part started as a 17.4 part coming out of the furnace fully annealed. So that means 25, 22, 25 Rockwell C. After H hardening, the entire gear was got to 43 Rockwell C. Quite hard. But that's not enough. And so the part was then plasma nitrided. So it's a case hardening process where you have a gas that interacts with just the top surface and forms almost like a ceramic. So this nitride that's winds up being a 64 Rockwell C, not throughout the entire gear, but just at the interface of the teeth where all the action is. And so for that 1/10 of a millimeter, it's 64 Rockwell C. So it's kind of an extreme example, but of what you can do with these parts that start out relatively soft. All right, switch gears. Now let's talk a little bit about wire brushing. This is one of the easiest, quickest ways to deburr, blend edges, remove surface imperfections, remove oxide. So this thing, I use that on my barbecue grill, but you might want to use it on your metal printed parts. We do. So here's an example of a copper heat exchanger. You know, copper develops a nice patina over time. If you want this to be a shiny, red, beautiful copper, just give it a few brush strokes. And you can do a variety of things. It doesn't have to be this manual process. You can buy a bunch of these brushes, put them on a drill, and make it even easier on yourself. Or you can have a little table setup for $100 on Amazon. This wire wheel can be used. So here's examples of wire brushed gears, and here's this example. Same heat exchanger with on the display. It's got less of this patina because it was wire brushed. Moving along with a couple more examples, you got polishing, buffing. Polishing is a process that is abrasive, where that abrasive is glued to the work wheel, whereas buffing is a loose abrasive applied to the work wheel. And so with polishing, it's a more aggressive process, buffing less harsh. And you can use them in a combination. You know, if you want a mirror finish, you can do polishing and then buffing. And you can, depending on what kind of finish you want, what kind of characteristics the part has, you can use a variety of kind of formulas. You can use rough abrasives, you can use finer abrasives, or even buffing wheels. You can do this with whether it's Dremel tools, where you have kind of disposable abrasive wheels. You can do soft deburring wheel, again on the same benchtop model. This is a relatively easy thing to run. All of these solutions you can get for under $100 and have a nice buffing, polishing wire wheel setup really inexpensively. So what's the bottom line? The bottom line is you can 3D print amazingly complex parts. Let's see, are there any that I didn't show? You know, you can do cool gears, you can do geometries you can't mold or machine because they're so complex. They're assemblies. You can do small parts, large parts, parts that normally would be several parts together. Some more examples of impossible geometry. So this is a fuel atomizer with the internal slotted channels that curve. So you can print a whole bunch of amazing complex parts, and your favorite metal processing methods are entirely applicable here. So there's a ton of post-processing possibilities, and there's the familiar trade-offs with costs and capital equipment, what you want functionally from the part, and processing time. So it is very likely that if you need a particular finishing method, there's going to be a technique that's entirely applicable to the 3D printed parts. So if any of the stuff that we covered today sounds relevant, we'd welcome an opportunity to chat with you, look at your applications, and see if there's a 3D printing system that may be a fit for you. And if so, you know, provide a benchmark part with all the metrics on what it would take to produce it, throughput, cost, etc. So with that, I'm going to take a look at whether there's any questions left, and if not, you'll be free to go. So let's see if there's questions. So in your quality measurements, what is the preferred method? Is X-ray for internal imperfections the preferred method or something else? Also in regards to when to do the QA, is it after the surface finish process or before? Okay, a couple questions in there. First of all, if you got to X-ray the parts, So during development, of course, we X-ray the parts, EDX, do cross-section, do surface analysis. So really understand what are the imperfections. The parts are polished. We look at the grain structure, the phases. All that is part of the the material science involved in developing these. That said, hopefully that's something you either never do or do once. This is not something, if you got to X-ray parts as they come off the assembly line, that process is probably not robust. The whole point of the couple hundred people that work here at Desktop Metal is we develop the process, the equipment, so that you don't have to X-ray the parts. And so really the QA that's necessary typically is, hey, you printed the part. Does it meet the dimensional characteristics? Either throw a micrometer onto the key dimensions, or you could scan the parts and see, does it what is the overlap between the geometry you requested and the geometry you got? Is it to spec? Is it just a scaling thing? Is it on target? Is it a little too large, too small? And those things are very easy to then dial in the printing process. So we might be shooting for better than 1%, but if you notice that time after time you're 0.5% lower than what the part needs to be, you can scale the part up by another 0.5% when you're printing it, so that once it shrinks, it's the right dimensions. All right. As far as the surface finish process, let's see. The question is in regards to when to do the QA. Is it after the surface finish or before? Well, the answer is it depends what you need. If you want to do dimensional tolerances, then you probably want to measure it on the final part. So let's say you have a piston head and you've machined the outside. What you care about so that it fits in the cylinder is the dimensions after all of the machining or polishing. But you also probably want to, if you're going to do some post-processing, let's say electropolishing or let's say vibratory bowl process to smooth out a part, you probably want to measure a few of the key dimensions before and after. So you develop a sense, okay, this process takes off 0.5 millimeter, it takes off 0.010 of an inch, and so I'm going to make the part that much bigger, for example, or offset some surfaces. All right, hopefully that shed a little light on that. Let's see if there's any other questions. There's no other questions. Well, I'll wait a couple more seconds. Otherwise, thank you all very much for your time.